Welcome students to IIT PAL problem solving session. Our topic is probability and this is lecture number 2. In the last class, we have given you two formulae. So, let us recollect them. One is that if we have n identical balls which are to be kept in k boxes such that no box will remain empty, then the number of possible arrangements is n minus 1 C k minus 1. For example, if we have 3 identical balls to be kept in 2 boxes such that no box is empty, then there are 2 possible ways of doing it. One in the first box and 2 in the second box, or 2 in the first box and 1 in the second box. And the second formula was similar setup, n identical balls to be kept in k boxes such that some boxes may remain empty, then the number of possible arrangements is n plus k minus 1 C k minus 1. Example, 3 balls, 2 boxes. Therefore, possible arrangements are 0, 3, 1, 2, 2, 1 and 3, 0, that is equal to 4, and we have three plus 2 minus 1 C 2 minus 1 is equal to 4 C 1 is equal to 4. So, application: in how many ways you can choose five numbers A, comma B, comma C, D and E such that each one is greater than 0 and A plus B plus C plus D plus E is equal to 20, then the number of possible solutions is, as you can well understand, it is going to be 20 minus 1 C 5 minus 1 is equal to 19 C 4. However, if A, comma B, comma C, D and E are greater than equal to 0, then the number of possible solutions is 20 plus 5 minus 1 C 5 minus 1 is equal to 24 C 4. And how to get that? We can assume that we have 20 balls which are identical, or we can say I have 1 1 1 up to 20 times, and we are splitting them into 5 compartments by drawing such lines which I have explained in the last class. Then the sum of ones in a particular box will give you the corresponding number. Since there are 20 ones, the sum will always be 20, and each one of them you can say this is A, this is B, and like that this is going to be E. So, there we can understand that we can solve these problems using the above formula. Now, let us consider a slightly difficult problem. So, problem: in how many ways you can choose five numbers N1, N2, N3, N4 and N5 such that Ni greater than 0 for all I is equal to 1 to 5 and N1 less than N2 less than N3 less than N4 and that is less than N5, and sigma Ni I is equal to 1 to 5 is equal to 20. So, this problem is slightly different. As you can understand, here we are looking at all the 5 numbers will have to be different, that is, a number cannot be repeated, they are all greater than 0 and their sum is 20. So, let us understand the problem. One possible solution is 1, 2, 3, 4 and 10. This is a possible solution because all 5 are distinct, but 1, 2, 4, 4, 9 is not a solution, since 4 is repeated. So, I hope the problem is clear to you. So, let us go for solving it. Solution. Note that smallest possible value for n1 is equal to 1. For n2 is equal to 2, because n2 cannot be 1, since we know n1 is smaller than n2. And similarly, for n5 this is equal to 5. Therefore, let us define 5 new variables x1, x2, x3, x4 and x5 as follows. x1 is equal to n1 minus 1, x2 is equal to n2 minus 2, x3 is equal to n3 minus 3, x4 is equal to n4 minus 4 and x5 is equal to n5 minus 5. Therefore, each xi is greater than equal to 0 and x1 less than equal to x2 less than equal to x3 less than equal to x4 and less than equal to x5. Hence, the problem becomes to choose five numbers x1, x2, x3, x4 and x5 such that all are greater than equal to 0 and x1 plus x2 plus x3 plus x4 plus x5 is equal to n1 minus 1 plus n2 minus 2 plus n3 minus 3 plus n4 minus 4 plus n5 minus 5 is equal to sigma ni I is equal to 1 to 5 minus 1 plus 2 plus 3 plus 4 plus 5 is equal to 20 minus 15 is equal to 5. So, we can start as follows: x1, x2, x3, x4 x 5, their sum will have to be 5. So, one possible solution is 0, 0, 0, 0 and 5. This gives us the solution 1, 2, 3, 4 and 10. Next one is 0, 0, 0, 1, 4. Therefore, this gives us the solution 1, 2, 3, 5 and 9. 0, 0, 0, 2, 3. Therefore, we get the solution 1, 2, 3, 6 and 8. Since we cannot decrease from x 5 and give it to x 4, so we go like this, we put 1 here. Therefore, x 4, the smallest value is going to be 1, therefore, we are left with a 3 here, and therefore, the solution that we get is 1, 2, 4, 5 and 8. Next one is 0, 0, 1. We decrease from 1 from here and add it here, therefore, we get 2, 2. Therefore, the solution is 1, 2, 4, 6 and 7. Next, what we can do, we now make this to be 1, therefore, we get 0, 1, x 3 cannot be less than 1. So, smallest value is 1, x 4 again we give 1 and we give 2 here. So, that makes it 5 and corresponding solution is 1, 3, 4, 5 and 7, and finally, we get 1, 1, 1, 1 and 1, and the corresponding solution is 2, 3, 4, 5 and 6. Note that all of them will sum up to 20. Therefore, number of possible solutions is 7. I hope you understood the technique, but let me solve a very similar problem so that you understand it. So, problem is, in how many ways you can choose four numbers n1 less than n2 less than n3 and less than n4, that is they are all distinct, n greater than 0 for all I is equal to 1, 2, 3 and 4, and sigma n I is equal to 1 to 4 is equal to 16. So, that is the problem. So, again as before, we define x 1 is equal to n 1 minus 1, x 2 is equal to n 2 minus 2, x 3 is equal to n 3 minus 3 and x 4 is equal to n 4 minus 4. Therefore, such that each xi is greater than equal to 0, x1 less than equal to x2 less than equal to x3 less than equal to x4, and sigma xi is equal to 16 minus 10 is equal to 6. Therefore, we go as follows: x1, x2, x3 and x4. Again we generate them very systematically. We get 0, 0, 0, 6, 0, 0, 1, 5, 0, 0, 2, 4, 0, 0, 3, 3, 0, 1, 1, 4, 0, 1, 2, 3, 1, 1, 1, 3, 1, 1, 2, 2, and we can see that we can also do 0, 2, 2, 2. So, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 9 possible solutions. I leave it with you that given the arrangement of x1, x2, x3 and x4, we try to find out what is going to be the set n1, n2, n3 and n4. Now, one problem is, how do you know that this is a complete set? It could happen that you might have missed some of them. Therefore, it needs a mathematical way of doing this. This you can do using binomial theorem. I want you to think about it. In some of the later lectures, I shall take up the problem and I will show you how you will be confident that you have taken care of all the possible arrangements of x1, x2, x4. Okay? So, for the time being, let us now focus on probability. We know that we talk about probability when the underlying experiment is random. Therefore, the sample space omega is known, and we need to compute probability of what? That is the question. If we look at some of the random experiments that we described in the last class, then we see that suppose we are looking at coin tossing, say 5 times, we may look at what is the probability of two heads, or say something like what is the probability of the number of tails is prime. Similarly, if you remember, we talked about the problem passengers with bags. So, some of the probabilities that we may look for is what is the probability that number of bags is even, or say number of passengers is odd, etc. If you analyze these type of problems, we understand that given sample space omega, we are looking at a subset of it and we are trying to find out its probability. So, this is what is very important, and in mathematical terms we call it an event. What is an event? An event is a subset of the sample space omega. Why? Consider the coin tossing problem, and suppose we toss a coin 3 times. And we want to compute that number of heads is odd. We have seen that there are 8 possible outcomes, of which we are looking at number of heads is odd, that is number of head is 1, that can be done in these following ways: H T T, T H T and T T H, and number of head is 3, that is in one way H H H. Therefore, we are looking at the probability of the subset H T T, T H T, T T H and H H H. Okay? So, now you understand the concept of an event. Some definitions: these subsets of cardinality 1 are called elementary events. That is, the outcome of one individual trial is called an elementary event. Therefore, if we throw a die, then number of elementary events is 6, that is 1, 2, 3 up to 6. An event comprising of more than one elementary event is called a compound event. Example: suppose the omega is the set 1, 2, 3, 4, 5, 6, 7, 8, 9. How many compound events are possible? Since cardinality of omega is equal to 9, therefore, there are 2 to the power 9 possible subsets, of which one is phi, that is a null set, and 9 are elementary events. Therefore, number of compound events is 2 to the power 9 minus 9 plus 1 is equal to 512 minus 10 is equal to 502. So many compound events are possible. Some other definitions: two events U1 and E2 are said to be disjoint if U1 intersection A2, U1 intersection E2 is equal to phi or empty set. Example: throwing a die, U1 is getting a number less than equal to 3. E2 is getting a number greater than 4. You can see that these are disjoint. A sequence of events say E1, E2, Ek is said to be mutually exclusive if Ei intersection Ej is equal to phi for all I comma j belonging to 1, 2, 3 up to k and I not equal to j. Another important definition is two events A and B are said to be independent if probability A intersection B is equal to probability of A into probability of B. Now, you may ask me what is probability? Of an event? That is the question. So, probability is a mapping from the power set of omega to 0, 1. That is, if A is a subset of omega, then P of A is the probability associated with the event A is a number P such that 0 less than equal to P less than equal to 1, where P satisfies the following: A, P of A is greater than equal to 0 for all A contained in omega. B, P of omega is equal to 1, and C, if A1, A2, AK are mutually exclusive, then P of A1 union A2 union AK is equal to sigma over probability of individual event I is equal to 1 to k. So, these are the basic definitions which allow us to compute probability. In general, given a set A which is a subset of omega, probability of A is computed as number of elements in A divided by the cardinality of omega. Example, throwing a die and probability of getting an even number is cardinality of 2, 4, 6 divided by cardinality of omega is equal to 3 by 6 is equal to half. Suppose probability of getting a head is p when 0 less than p less than 1. Then what is the probability of getting 2 heads in 3 tosses? How to obtain such a probability? In order to solve that, let us first understand a few properties. So, show that probability of A complement is equal to 1 minus probability of A. This is true since A union A complement is equal to omega. Therefore, 1 is equal to probability of omega is equal to probability of A union A complement is equal to probability of A plus probability of A complement. Therefore, probability of A complement is equal to 1 minus probability of A. Therefore, when we are tossing a coin, if A is equal to getting a head, then A complement is equal to getting a tail. Therefore, if probability of head is equal to P, then probability of tail is equal to 1 minus P. Now, consider getting 2 heads in 3 tosses. This event can be broken down into probability of H T plus probability of H T H plus probability of T H H. Now, what is the probability of H H T? That means probability of getting a first toss to be head, the second toss to be head and the third toss to be tail. What is the probability? Probability of getting a head in the first toss is P, that multiplied by probability of getting a head in the second toss is P, and this one is 1 minus P. In a similar way, this will give me P square into 1 minus P, and this will also give me P square into 1 minus P. Therefore, total probability is equal to 3 P square into 1 minus P. That is how we arrive at the solution. Another important property is probability of A union B is equal to probability of A plus probability of B minus probability of A intersected with B. This can be shown like this. Consider this to be my omega, and suppose this is A and this is B. Therefore, A union B is this plus this. So, this we can write it as probability of A union B is equal to probability of B intersected with A complement plus probability B intersected with A plus probability A intersected with B complement. Because these three are disjoint. Now, probability B intersected with A complement, which is this part, is equal to probability of B minus probability of A intersected with B, because we are subtracting this part from the probability of B, and probability of B intersected with A plus probability A intersected with B complement is equal to probability of A, because we are adding these two parts. Therefore, together we have probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. This is one property we will use in solving problems. Now, let me solve another problem. Suppose E is a random experiment let A and B be two events such that 0 less than probability of A less than 1 and 0 less than probability of B less than 1. Then which of the following statements are true? A and A complement are mutually exclusive. B, A and A complement are independent. C, A and B are independent implies A and B complement are independent, and D, A and B are independent implies A complement and B complement are independent. So, these are the 4 statements given. We have to check they are true or false. A, it is obvious that A and A complement are mutually exclusive, because if this is my omega and this is my A, then this part is A complement, since there does not exist any omega such that omega belongs to A and omega belongs to A complement. B, A and A complement are independent. Now, we know that A and B are independent if probability of A intersection B is equal to probability of A into probability of B. Now, probability of A intersection A complement is equal to 0, since A intersection A complement is phi. Therefore, its probability is number of elements in phi divided by cardinality of omega. Is equal to 0. However, probability of A into probability of A complement is not equal to 0, since 0 less than probability of A less than 1. Therefore, B is false. see, A and B are independent implies A and B complement are independent. Now, probability of A intersection B complement. So, if we draw it, suppose this is omega, suppose this is A and suppose this is B. Therefore, A intersection B complement is this part is equal to probability of A minus probability of A intersection B, because this is A and this part is A intersected with B, therefore, we get it is equal to probability of A minus probability of A into probability of B, since A and B are independent, is equal to probability of A into 1 minus probability of B is equal to probability of A into probability of B complement. Therefore, A and B complement are independent. Therefore, C is true. What about D? A and B are independent implies A complement and B complement are independent. Now, probability A complement intersection B complement, if we draw the similar type of diagram again, and this is A and this is B, then A complement intersection B complement is this part is equal to probability of omega minus probability of A union B is equal to 1 minus probability of A plus probability of B minus probability of A intersection B is equal to 1 minus probability of A minus probability of B plus probability of A intersection B is equal to 1 minus probability of A minus probability of B into 1 minus probability of A, since probability of A intersection B is equal to probability of A into probability of B is equal to 1 minus probability of A into 1 minus probability of B is equal to probability of A complement into probability of B complement. Therefore, A complement and B complement are independent. Okay, friends, I stop here today. in the next class I shall start with events and will solve several problems involving algebra of events and to see how to get probabilities of different events. Okay friends, thank you.